Fantastic. So thank you so much, John, for the invitation. Thank you for having me here. It's great to be in Oxford. I was saying that I haven't actually visited the Mathematical Institute building before, so this is new for me. Right, so I should introduce myself and my background a bit more, since I don't sound perhaps like a typical mathematician. So I'll tell you a bit about my background first before we talk about sort of the ethics of modelling and what that means. So I studied physics and then maths, and then I went to do a PhD in climate modelling because I thought, let's do something useful with this, let's do something interesting. And I liked fluid dynamics, so I thought the fluid dynamics of the atmosphere would be a good place to start. And so I signed up for a PhD on North Atlantic storms. What's going to happen to those North Atlantic storms in the future given climate change? So we're familiar with the sort of extreme events that happen in autumn and winter in the UK and in Europe. That's the kind of event that I was interested in, like Storm Dara that we had last year that was very damaging. And so the first thing that I did when I started my PhD was a literature review. I went to look at the literature, at what other people had found, at what other models had found would happen to these North Atlantic storms. And so I sort of dutifully went through and tabulated all of the recent results. And what I realized as I started to do that was that actually there's quite a lot of research, quite a lot of different models, statistical models, dynamical models, ones that take different approaches, and they model the storms in quite different ways. And what I was hoping to see was this kind of building up a picture towards some level of confidence towards what we know. But what I actually found was that they all said different things. For models that said the storm tracks would move northwards, there was another that said they would move southwards, that they would get more frequent or less frequent, or more intense or less intense. And you know, although there weren't necessarily formal error bars on all of them, where there were some uncertainties indicated, they were kind of outside the range of each other's uncertainty. And so what do I conclude from that, or what did I conclude from that? I suppose I realized that I hadn't learned very much about North Atlantic storms, and I hadn't learned very much about climate change, but maybe I'd learned quite a lot about models and the way that we make models and use models, and perhaps have a tendency to be a little bit overconfident in the outputs of our models. And so then from that experience, I mean, and of course my PhD supervisor then said, don't think about that, Erica, just, you know, go and finish these models, do some statistical models, look at some dynamical models, and write a thesis about modeling. And I did. But I kind of couldn't tear myself away from this idea that actually, how do we quantify the uncertainty in the output of the model? What even does the output of the model actually mean? Because the model isn't perfect. The model is a simplification. In what ways is it simplified? We have lots of different models, and they've all been simplified in different ways. So how do all these different simplifications and abstractions, how do they actually correspond to the real world out there, which is the thing that we care about, not the computer? And so from there, I then spent, I guess, 10 years or so working on a series of short-term projects in primarily weather and climate, looking at the use of models to inform decisions for different applications, such as energy, insurance, humanitarian decision-making. You know, how do we decide what to do on the basis of these forecasts, usually at a shorter timescale than climate? And so as I did that, I guess I kind of kept running into these same questions. What does the model output mean? What is it? How do we go from, you know, this thing that's in our computer to make inferences about the real world? How do we make statements that we actually believe from the output of this model, if the models are all wrong? You know, I'm sure you've all heard that famous quote from George Box that all models are wrong, and of course, comma, but some are useful, which undeniably they are. But how? How can they be useful when they're wrong? How do we understand that? And so I kept coming back to this. And then, of course, there was this incredible example of models being used to support decision-making live. And that was, of course, the pandemic, the COVID-19 pandemic. And we saw in the early days, in February, March 2020, that there were models like the one at the bottom left here, which I'm sure you've all seen before. Epidemic models, thinking about how is this infection transmitted between people? How much do we expect it then to go up? What will the rates be in the population? What will the consequences be for hospitalization? And of course, we can model all of these things. We can make assumptions, make simplifications, and put that into a model and come up with some outputs. And then we hope that that will influence decision making, right? We want to be able to go and say, hey, policymakers, decision makers, ministers, civil servants, look, I'm a mathematician, I've made this model. It tells us something about reality. We need to take some actions. So we are engaging again with the real world. And the models, of course, are not used just in that very linear kind of idealized concept of how decision making works. You don't just go away and do your maths and then sort of throw it over a wall and the decision maker goes, thank you very much, here I go, off to make my policy. It's more of a dialogue, right? There were rooms in which this was discussed. It was very much a dialogue, and the model was at the center of how that dialogue happened. The decision maker might say, oh, that's really interesting, but what I'd be interested in is, I don't know, a regional breakdown. Can you tell me how this is different in different areas? Or can you tell me what would happen if we took this policy intervention rather than that one? And so the models were used, as a communication tool between scientists and decision makers. And then, of course, as we're all familiar with, they were also used as a communication tool between scientists, decision makers, and the general public. And so, again, we're familiar with graphs like the one on the right here, this little GIF. The idea of flatten the curve is a concept that has kind of come directly from epidemiological modeling. That you can see there's a family resemblance there between those pictures. That didn't come out of nowhere. It came out of the modeling and the academic environment, and somehow it was translated in a way. It escaped into that public environment, and it was used by people who probably couldn't even necessarily tell you what the axes on the graph were or what they meant or attach any numbers to anything. And yet they used that as a way of understanding what the possible interventions might be and what the benefit of taking those interventions were. And so the models are also used in that kind of justificatory sense. You must take action, and you must take this action because of this information that I have from a particular model. Okay, so that sort of social aspect of the model, the way that the models are being used to communicate, to discuss, to inform, to justify, and also, depending on your point of view, to pressure, perhaps to convince, to coerce even. These models are used in many different ways which have ethical consequences, which I'll talk about a little later. And so while that was happening, the other thing that I was doing was kind of trying to write about all of these things that had bubbled up for me over the previous 10 years or so. And so this is my book, Escape from Model Land, which is really my attempt to kind of synthesize some of these, because coming from a sort of mathematical, physical science perspective to some inherently very social and political concepts, I felt that it was actually quite helpful to try to join those up a bit. So the book is really my attempt to join those up and to explain and articulate why I think some of these concepts are so important and why we as mathematicians need to think about that when we're in the process of making models. So what do I mean by model land? Model land, in my conception, is kind of where you are when you're inside your model. So you've gone away, you've written down a bunch of equations, maybe you've programmed them into a computer, or maybe it's just a flowchart on the back of an envelope. I'm fairly agnostic about types of models. But once you've done that, you have some idea of what your variables are and how they relate to each other in some perhaps very well quantified sense, perhaps a bit fluffy. And so when you're inside the boundaries of that, you are in model land. Everything works. You can you know, pick your initial conditions or your boundary conditions, you can run your model, you can get an answer. It's all nice and neat and clean and tidy, and it works, and you get something out of the other end. But nobody cares, nobody should care, nobody has any interest in what your model says until you make an assertion that the output of your model has something to do with reality, the real world, which is where we live and where we make decisions and where the things that we care about actually exist, not inside the model. And so we have to escape from model land, right? So that's the idea of the book. So how do we escape from model land? And the thesis of the book really is that there are two main ways to escape from model land. And the one that will immediately come to mind is data, of course. We go out, we take some data, and we say, is the model any good? Did it fit the past data well? But of course, as the sort of classic financial disclaimer goes, past performance is no guarantee of future success. So just because something did well in the past doesn't necessarily mean it's going to do well in the future. We have to make some kind of expert judgment about whether we think that the past, the performance in the past is going to reflect performance in the future. So, for example, if we're thinking about the weather forecast, if you get your phone out of your pocket and look at the weather forecast, you understand how good it is. You also know that it's not perfect. But you have a good intuitive understanding that tomorrow's weather forecast is pretty reliable. Weather forecast for 3 or 4 days' time may be less reliable, but still useful. And the weather forecast for 3 weeks' time, no use at all. And that's because you have, you could go and look at the Met Office statistics of how good the model is, because it's had lots of opportunities to make out-of-sample predictions and to check those and to run some kind of forecast evaluation metric and to tell you exactly how good it is and when it is good and when it's not good. But also you've got experience, you've looked at the weather forecast before. And so you have developed an understanding yourself of how good it is and when it's good and when it's not good. But if we're thinking about predicting something further into the future, or if we're thinking of predicting something that has any social component, if we have humans in a system, then the behavior of humans in the past is a moderately good guide, but humans can always be strange creatures and go off and do something completely unexpected. So if we were trying to forecast, for example, the financial markets, we might suddenly be surprised by an event like the 2008 financial crisis. The past performance, the models that did really well in just before 2007, 2008, suddenly didn't do well. So we expect that there might be things happening that are going to be relevant now or in the future that were not relevant in the past. If we think about the weather model, of course the weather models are really quite good and well calibrated, but if we want to run essentially the same model, climate models are very similar to weather models. They're based on the same equations. There are differences, there's more that goes into them. But should we expect them to do well on the 21st century climate, given that they've been calibrated extremely well to 20th century climate? Well, not necessarily, because the one thing we know is that the climate is changing, that there is a significant change to the underlying kind of regime and structure of what's happening, the parameterizations perhaps that we have developed for the physics of the model on the small scale may just not be relevant anymore in a different climate. We don't know. We have to make an expert judgment. So we have to look at that model and say, do I think that it captures the relationships adequately? Do I think that the relationships that it has captured and perhaps that I have been able to evaluate in the past are going to remain the important ones that work in the same way in the future? And there is no way to do that inside model land. There is no way to do that with respect to data. You have to make a judgment. You have to make a call. You have to decide yourself personally whether you think that that's what's going to happen or not. So we could come back to that as well at the end, because obviously there are different degrees of that. We all agree on the laws of physics, but maybe we don't all agree on cloud parameterization schemes in atmospheric physics models. There could be differences of opinion there, even if we did all agree on the laws of physics. Okay, so that's escaping from model land, and so I've sort of sketched that difference. I mean, there's two ends of a spectrum there, and really we always need to use both. Hopefully we always have at least some data, and we're not totally in the dark and we've written down something completely arbitrary. But we're always going to need the expert judgment as well. So based on that, then I would distinguish two different kinds of models, or two different kinds of sort of modeling situations, not necessarily the model itself, but the model applied in a particular way. So if we have some data and we choose to fit a line through those points, we might just kind of draw a straight line. Fine. So that's one assumption about the functional form of the model that is trying to fit the data. Or we might fit a quadratic. We might draw that line and then say, oh, but actually it tips up a bit at both ends, so I'm going to fit a quadratic instead, and maybe that would be a bit better. And I suppose what I want to say is that when you're inside the kind of envelope of calibration data, right, the observations that you've seen that you're fitting this model to, it doesn't actually really matter a great deal whether you chose to fit the linear or the quadratic. You're still getting more or less the same thing. But when you go outside that and you start extrapolating, it matters a very great deal, to the extent of going off to infinity in different directions. So inside here, when we're basically interpolating, we can be completely data-driven. And that will be fine, because the assumptions that we're making about functional form are probably not going to have a massive impact. You know, we're going to be pinned back to those data, regardless of what we try to do, assuming we've got enough data. It might be that we only have 3 data points. In that case, we can't do anything. But if we've got enough. But then when we go outside there, when we start extrapolating, of course, we should always be careful when we extrapolate. But at that point, we are in what I call an assumption-driven regime. We're trying to do something, and the answer that we get is primarily determined by the assumptions that we made about functional form, the expert judgments that we made. You know, we probably impose either a straight line or a quadratic based on our expectations of how this system works. And I haven't told you what the axes are, but imagine your own favorite, you know, set of data. It could be something completely different. Maybe it would make sense to fit an exponential. Maybe it's something that can't go below 0. Maybe, you know, all sorts of constraints might be there. But then you're making assumptions, you're fitting that thing, and when you go outside your calibration data, then it really matters. Okay. Some kinds of examples, so data-driven models, and if there's anyone in the audience that does a bit of AI or machine learning, this will be something we can come back to at the end again. If we're in the data-driven regime, we can expect to get good performance, and we can expect to sort of quantify our uncertainty with reasonable accuracy, you know, relative to the data that we've got. So that could include things like the weather forecast, the example I just gave, ballistic motion, like if I throw a ball to you, there's all sorts of complexities about friction and air resistance, but in principle we could do all of those things, and we could take enough data, and we're not going beyond the realm of the calibration. But in the assumption-driven regime, we've got things like energy policy, we've got pandemic, you know, long-term pandemic projections. Who knows what's going to happen? We've got financial markets, we've got elections, we've got things that really matter. You know, we've got climate change, things that have big consequences. And so we have to be, I think, a little bit careful about not allowing the well-warranted and justified confidence that we have in models that perform well in the data-driven regime to kind of give us overconfidence in this assumption-driven regime. I think that's quite dangerous. But equally, we have to be careful that the difficulties that we have predicting in that assumption-driven regime don't contaminate our justified confidence in the other kinds of models. And those other kinds of models really are what the modern world is built on. All of the technology that we have is based on the fact that our mathematical models are incredibly good and they work really well. And so there's opportunities here as well as things to be careful of. Right, so I promised to talk about ethics. So I'll say something about values in models. Okay, so let's take an example, and we'll go back to this pandemic model that hopefully everybody is at least vaguely familiar with. So where are the ethical components of this? You know, somebody's gone away and they've taken the data that they happen to have and they've made the best possible model. So I am absolutely no disrespect here to the people that have made this model. I just want to highlight, you know, where the ethical and social components come in. So we have, you know, we've done this, but whose judgments are being represented here? Who's decided what are the four lines on here? You know, what are our options? Do nothing. Okay, I mean that's the sort of default option, so that's fair. But then the choice for taking policy options, somebody has decided what are the reasonable policy options here. Now, to take a completely ridiculous example, if this were an animal disease, then the options would include culling all infected individuals within a 4-mile radius of an outbreak, for example. And of course, that would be completely unacceptable in the case of a human disease, but that is a moral judgment. You know, it's an ethical judgment, which is now inside the model. To take another example, you know, this model is, you know, by its nature, extremely aggregative. It's put everything together into one. This is the whole of the UK population. But supposing we were to break that down into geographical regions, maybe we would see something different. And if you look at the pandemic flu models on which these COVID-19 models were based, there's a nice animation accompanying one of the older papers, which shows how if a pandemic is sort of seeded with lots of individuals arriving in a country, they've got a picture of the US and the UK, I think, then how does that progress? So the animation shows that you start with a few and then it sort of bubbles up and you have more. And at its height, that pandemic is then basically just a graph of population density because it infects some proportion of the population and then it goes back down again. Now, that's not at all what we saw in the pandemic, is it? What we saw actually was that there were geographical, kind of social, demographic, economic factors, which meant that some parts of the population were more vulnerable than others. And those were not geographically homogeneous. So we saw that the infections were high in certain areas for a time, and then it got lower, and then it would be high in another area, and then get lower. So, you know, the point is not that we should have had a model that could do this, but that if we had a model that could do that, it would have led us to think in a different way about perhaps the kinds of interventions that we might make. And perhaps the reason that we didn't make the model in that particular way is because we didn't have the data that would have supported making the model in that particular way. And the fact that we didn't have the data means that, you know, somebody maybe didn't consider it important enough to think about going out and getting that data. And of course, in an emergency situation, data is always going to be difficult to get anyway. So there are lots of ethical implications, is what I'm saying, of making a model in a certain way, even when that's the default way, even when you're just doing what somebody else did 5 years ago and you're applying the same methods and you're fitting it as best you can with the only data that you've got, there are still social and ethical implications, even if you didn't impose them yourself deliberately. Okay, so another example. So this is a set of 6 integrated assessment models. This is quite an old picture now, but it shows on the left some baseline scenarios of where do we get our energy from in 2100, given that we, you know, just carry on as we are. We're not making any special effort to meet carbon reduction targets. And then on the right, if we do, and we go for 2 degrees, as the Paris Agreement commits us to, if we have to get to 2 degrees, then we have to reduce, as you can see, coal, oil and gas are the kind of grey, red, orange bars here, and they've obviously reduced a lot in order to decarbonize, to make that pathway work. Okay, well, so far so good, but where are the ethical implications of that? Somebody's just gone out and they've made this model as best they can. Well, I think we have the same questions. I think we have the same questions coming up again as we saw in the example of the pandemic model, because somebody has made some judgments here that go into this model. For example, about the relative cost of different technologies. What's going to, how much is it feasible for the cost of fossil fuels to increase given carbon taxes? That's a political question. How much is it feasible to expand biomass? That's a sort of technical and political question. What about nuclear energy? If you're a modeling group based in Germany, you might have quite a different opinion of what is politically feasible, technically feasible, than if you're a modeling group based in France on nuclear energy, and you may then get completely different answers. And so there are value judgments embedded inside these models. There's also a question, again, the pandemic models didn't disaggregate, for example, by race or age or gender or social class. These models, for example, don't include things like behavior change. So what we're seeing in these models is that essentially they're cost optimizing, right? So they say we are where we are and we want to get to 2100 for the lowest possible cost. Well, ding ding, there's a value judgment to begin with, but let's put that to one side for a minute. And then we make assumptions about the cost of these different technologies, and sort of obviously, there's a lot more going on behind the scenes, but the ones that are cheaper, there'll be more of, and the ones that are more expensive, there'll be less of. And if you don't put, so behavior change, if you were to put behavior change in at a cost of, $1 per ton of carbon avoided, then it would be very popular. There'd be loads of it. We would just spend that money doing behavior change and reducing our energy demand. If you put it in at a cost of $200 per ton of carbon avoided, then there won't be very much of it because other energy technologies are cheaper. So if you don't put it in at all, what is the assumption? The assumption is that behavior change has an infinite cost, and therefore it's not going to happen at all. And that, I think, is a very strong value judgment. So we have to think, not just about what is in there, but also about what's not in there. What have we decided to exclude from our models? Okay, so now the maths. Right, you were all waiting for the maths. So a bit of Bayesian statistics for you. Don't worry, no equations. So models, here's a set of 7 models. Don't worry, no equations. And I suppose going back to my sort of observation as a PhD student, one of the problems that we have is that models tend to look like each other, because we are trying to model the same thing. So hopefully we've gone away, we have all made a model of something. So maybe I have something behind a curtain, and here are your 7 models of it. So what can you deduce about reality from this set of 7 models? Anyone want to shout out? What would you tell me about reality? Here's our set of models. Cat-shaped, great. Anything else?
All cats are stripy.
All cats are stripy. Are they all stripy? Maybe. No, that one's spotty. But so this isn't a sample of reality. So you're not deducing that all cats are stripy. This is a set of models of reality to which you don't have access. Okay, so reality is an object behind a curtain. And here are the models that we have of it. So anything else? So we might say it has 2 ears, whiskers, 2 eyes, a nose, a tail, although we can't see the tail on all of them. So perhaps we can't, but maybe we think actually that's consistent with having a tail, even though we can't see it there. Furry, yeah. Perhaps there's a range of colours that we think might be plausible. So we look at the similarities between our models, and we look at the differences between the models, and we try to sort of say, well, what do these all have in common? What do we think reality hopefully looks like? Okay, but we wouldn't just look at our set of models. We would go out and take some data as well. So because this is a nice thought experiment, I can show you the data. Here's the data. but you can't have all the data. You never get all the data, sorry. So you've taken that data, okay, and we've got something that looks like a tail, right? So we're going to go back to our models and confront the models with data. Right, so what have we learned? What would we do next? So for anyone who does work with like ensembles of models, which means just a set of models, a group of models, what might we do now? Well, we might say, okay, there's our reality. So we want something that looks as close as possible to reality. We want to calibrate the model to reproduce the observations. So we go back and say, right, which one is most consistent with the color, the fur length, the length of the tail? None of them looks perfect, but maybe that one at the top right looks kind of most plausible. So we might select the best model and say we will use that to make inferences. We'll decide that reality looks like that one. Or we might say, well, you know, maybe we don't want to jump to hasty conclusions. Maybe instead we will just rule out 2 or 3 of them as being inconsistent with the observation that we've taken, and perhaps we'll take a weighted average of the others, or do some kind of complicated process where we assess the degree of agreement between the data and the individual models. Perhaps we use some kind of information criteria. There are lots of different methods here. And then we're going to try and use that remaining set to make some inferences about reality. Right now, but because this is just a slide, I can show you what reality looks like. Right, I think half of you knew where I was going before I put that up. But so reality is not a cat. I mean, and this is the problem, right? That we tend to be overconfident with our models. We tend to, if we have a set of models, they tend to look more like each other than they do like the real world. And they are structurally biased in some way. Okay, so what did we learn? Well, actually, that set of cats was pretty informative because it did have 2 ears and it was furry and it is kind of cat-shaped. You were right, but it's not a cat. So our kind of formal inference methods are not going to work, or they're not going to work trivially. You know, it's not simple to do this. We'd have to think quite carefully about how to make those work. And actually, we're going to tend to be overconfident. We're going to tend to create uncertainty ranges which are too narrow. But we did learn something useful about this dog. So let's think about decision making. If we were, I don't know, if you had to interact with this dog and you'd only ever met a cat before, you know, you're not going to have too bad a time. It behaves somewhat similarly. If you needed to feed it, you know, that dog will very happily eat cat food, guarantee it. If you were a vet who had been trained to operate only on cats, and the dog came in with something wrong with it, then, you know, most of the time, you've got a pretty good shot at dealing with whatever's wrong with it. So just because our models are wrong, and just because our statistical inference methods are formally invalid, it doesn't mean that we can't do anything useful. You know, these models may still be helpful. They may still help us to act in the real world, even though we can't perfectly model the real world. So, by the way, what would we need to do to make our set of cats more informative about this dog? Well, we don't want to go away and make a bigger and better and more detailed cat, because that will only be more accurately wrong. What we want to do is extend our ensemble. Yeah, we want to push the diversity of that model ensemble out, such that instead of a set of cats, perhaps we have a set of mammals. And if we had a set of mammals, then actually maybe those statistical uncertainty ranges would be reasonable. You know, maybe those confidence intervals that we form would actually contain anything relevant about the dog if we had a set of mammals. But of course, we don't want to go too far. We don't want that set to include a chair and the concept of happiness, because then we are not going to be able to infer anything remotely useful. So there's a expert judgment, again, about the degree to which we need to push our model ensembles out without going too far. And this, again, introduces value judgments, because how do you decide how far to go? That depends how sensitive you are to getting the answer wrong. Would it matter if you got the answer really wrong? You know, is this like nuclear safety, Or is it what color you're going to paint your house next week? And in one case, you get it wrong, no big deal. The other case, you get it wrong, end of the world. So obviously, most things are somewhere in between. But the choices that we make methodologically in terms of the statistical inference from our models and the confidence that we're going to end up having in those model outputs, it depends on how much we care about the answer. And that depends on who we are, and it depends on what we value. So it depends on us, society, and politics. Okay, so to say the same thing again in a slightly more mathematical way, if we think about model error, okay, so you've got your model, and it's wrong. It's never going to be perfect. So the model has some error, and the error term is probably just described by subtracting. And again, let's hand wave a bit and pretend that they're in the same dimensions and we can subtract them, but subtracting reality from model. So we get the difference. So if you're a statistician, right, how many statisticians do we have in the audience? Who would, yeah, a few, okay. So if you're a statistician, then you probably say, well, I've made the model and all of the stuff that I can see happening, I've tried to put into the model. And if I subtracted reality from the model and I got something with a pattern in it, I would put that into the model and I'd take it out, right? So then I would keep going until the error term, the residuals, are randomly distributed. And so error, reality minus model, is going to be some kind of statistical distribution, some kind of random distribution. And that's how you think about model error, and that's how you decide how to make your model better. Okay, but we're not all statisticians. So is there anyone in the audience who would identify as being more of a kind of dynamical systems person, a sort of nonlinear? Yeah, I see a couple of nods. Okay, so if you're more of a dynamical systems person, or maybe more of a physicist, then you look at reality, which is one giant dynamical system that we don't understand and can't fully measure, and we've got the model, which is another small but complex dynamical system inside our computer that we hopefully just about understand and can measure. And we subtract those, what do we get? We get another big complex dynamical system, but it's a really weird one. Yeah, so instead of having this sort of nice thing that we understand, we're going to get something that looks weird. It's got things shooting off in different directions. Some of it's positive, some of it's negative. Blech, we don't know what it is. But okay, so there were quite a few people who aren't statisticians or dynamical systems people. Supposing that you're a social anthropologist. Do we have any of those in the audience? No. Supposing that you're a sort of more of a humanities person, you're a social science person, then you look at reality as the same reality out there for all of us, hopefully. And the model is what we understood. The model is what the modeler saw, what they were able to measure, what they understood, the way that they thought, the way that, I as a modeler kind of projected everything that I saw into my own space. It's also a function of my constraints, my ability to measure, the size of the computer that I have available. And so the model is very much a function of me, which means that the error term also is very much a function of me. The error term represents what I didn't understand, what I didn't think was important, what I didn't care about, what I wasn't able to do in the time that I had available, what I didn't prioritize. And so the error term is really something that's very social and political. It's not just a mathematical object, it's also a social object. And so again, that's where the ethics and the values start to creep in. Why does the model error look like that? Why did we choose not to model those things and only to model these things? So, what about AI? I said I would come back to AI. So, I suppose what I wanted to say about AI is that then for me, this gives us a neat way of understanding when we should expect AI to be able to give us good, reliable results that are not fundamentally value-laden, which is when we're basically interpolating, and when we expect AI, if we start doing it, AI basically is fitting an unknown shape here to those data. And maybe you could work it out if you go and look at the objective function. I mean, that would be great. We can look at what it is. But then in the extrapolation, the uncertainty is going to be primarily determined by that functional form that the AI chose to fit. Well, how? Why? The objective function we could go and look at, and we can analyze it on these same kind of grounds. We can say, what are the values that are embedded in this particular objective function? And that would be great. But most people doing AI for real-world applications they are definitely not doing that. They probably don't even know what the objective function is because they've got something in a package off a shelf. The engineers have done it and they've gone out and applied it. We don't know what it is that we're optimizing. So how can we, responsibly, ethically understand what it is that we're doing here? And that doesn't take away at all from the immense opportunity that there is in the interpolatory space for AI to be world-changing and for it to do a great job of interpolating better than we can with, without a huge amount of data, but with a secure understanding that we're not going beyond the range of the calibration of this model. So there aren't any values here, or there isn't much. There are values and there are ethics insofar as somebody had to decide what data to get, and somebody had to decide what to work on, and somebody probably gave some funding for that, and they probably had an agenda. So those are all important ethical issues, and I don't downplay those. But what I want you to understand from my lecture is that there are more ethical issues that are more deeper in the mathematics. They are right in there in this objective function and in the way that we decide what we're choosing to do, and that mainly it matters how we apply these models, not what the models are themselves, but how we choose to apply them and the way that we choose to think about them. Okay, model evaluation briefly then. So this is kind of the same question. What makes a good model? Well, it's easy to kind of naively say, well, a good model is just one that represents the target well. I mean, yes, absolutely. But we need to have some kind of evaluation metrics to understand that. And so, the choice of how we are fitting, what do we do with these residuals in order to minimize them? That's your value judgment. So your value judgment is in there. And we might want to include more than just that performance. So supposing we are working on machine translation, and you want a model which is going to convert between a gender-neutral language and a gendered language. If you, in that gender-neutral language, say, they are a doctor, and it converts to he is a doctor. And if you, in that gender-neutral language, say they are a nurse, and it converts to she is a nurse. Well, it's doing that. It's relying on stereotypes because that performs best on the evaluation metrics. That's what stereotypes are. But that might not be a good thing to do. So we might want to include in the objective function something that recognizes that that isn't what we want to do. Okay, so this all sort of comes to science and society. Is science objective? Science certainly has a lot to say. It has a lot of power. It has a lot of authority in our society. People want to trust science. We want to understand science. We want to use science to make better decisions. And we can. And the scientific information will help us to make better decisions. But I think that relationship of trust is something that we need to be very careful with, because trust is hard to win and easy to lose. So I think we need to think quite carefully as modelers, as mathematicians, as scientists acting in society, and a society that is increasingly somewhat skeptical about scientists and the agenda of scientists. We need to be very careful about explaining when and how and why we should trust models, if we should, and when and how and why we should actually be quite careful, perhaps skeptical, when we should think carefully about about what it is that the model is actually saying to us. So this relationship of trust is related to mathematical concepts in forecast evaluation and model evaluation, but I hope I've also shown that it's a very social thing as well. It's a social and political thing. And so that I think if we can spend a bit of time thinking and talking about some of these concepts, that I think that will help to improve trust, and not just sort of, we must improve trust, but we need to talk, we need to have a science that is trustworthy, right? We need to genuinely be open to discussions about values. We need to not pretend to be totally objective. But we also need to not throw away the baby with the bathwater. This can be difficult to talk about, because if you start saying that there are values and politics in science, then there's a stream of society that will say, I knew you had an agenda. Off you go. We don't trust any of it. So, and this is a risk, this is a big risk, I think, right now, if we look at what's happening across the world. So it's incumbent on us as modelers to sort of explain and think carefully about where these issues are coming in, and to try to address them as far as we can. Right, and with that I will just plug my book again, where I have explored many of these issues. It's sort of my kind of attempt to work out for myself what I thought about some of these things. And I really hope that you'll join me in more conversation about these issues and where we go from here. Thank you.